Hi everyone! Today we'll take a closer look at Chapter 4, Test Analysis and Design. We will learn the section State Transition Testing in the topic Black Box Test Techniques. Let's begin. This video is a part of the ISTQB Foundation Level Preparation course on Udemy. For more information, check the description below the video. This time, we will not form a basic checklist of sequential steps for using the state transition test design technique. Instead, we will provide practical explanations for each theory paragraph in the syllabus. Let's start with the first paragraph. You can pause the video and read the text yourself. The text is written in such a way that it's almost impossible to understand what's it all about. In the new version 4.0 of the syllabus, the state transition testing is complicated by guard conditions and actions. We'll explain this a little later, and let's start with the basics of the theory. A basic state transition diagram model looks like this. It's very clear. There are three states: open, in progress, and closed. States can be marked with circles, squares, rhombuses, rectangles, etc. There are also three transitions. A transition is initiated by the event: start progress, reopen, close. Transitions are mostly indicated by arrows. The arrow starts in one state and ends in another. This demonstrates valid transitions. For example, the start state is open, the event is start progress, and the end state is in progress. This is only one valid transition with two states and one event. At this stage, everything is clear. Let's consider the next paragraph from the syllabus. Let's skip the second paragraph for now, and we'll come back to it a little bit later. Let's first deal with the state transition diagram. You can pause the video and read the paragraph dedicated to the test case. Let's write test for a simple diagram. The vast majority of test cases consist of a complete transition, having a start state, an event, and an end state as a result of the event. For example, the start state is open, the first circle. The event is start progress, the first arrow. And the end state is in progress, the second circle. As you can see, transition is now just an arrow. A transition is both a state and an event. And mostly one transition is just one step in the test case. One test case may, and usually will, cover several transitions between states. And each subsequent transition must start from the state at which the previous transition ended. For example, a complete test case will consist of two steps. The first transition from open state to in-progress state. The second transition from the in-progress state to the closed state. However, you will never see such complete test cases in ISTQB questions. Usually, the steps are marked only with the names of states and events. Mostly, the steps of the test cases are the names of the events. For example, start progress, close. This may confuse you, and you may think that this test only covers events. In fact, this is the same test that we just considered, which covers three states and two events, just written in a simplified manner. Another example of a test is the steps can only be state names, separated by arrows or commas. Again, this is an example of the same test covering two transitions. The first transition from open state to in-progress state. The second transition from the in-progress state to the closed state. That's all for the paragraph about test cases. Let's move to the next paragraph. It's all about the all states coverage. You can pause the video and read it several times, and we'll visualize it instead. In all states coverage, the covered items are the states. To achieve 100% all states coverage, test cases must ensure that all the states are visited. In our case, the states are marked with circles. As with equivalence partitioning, BVA, and decision table test design techniques, it's best to visualize the test coverage with a table. We simply write down all available states. We have three of them. After that, we write a test case, the same as in the previous examples. How many states do you think this test case covers? With two events, start progress, close. It covers all three states: open, in progress, closed. Accordingly, the all states coverage is 100%. You should learn how to expand tests from a list of events or states to full tests. With clearly written steps, then it becomes clear that the two-event test actually covers both states and events full of two transitions. Let's check the next coverage. The valid transitions coverage. You can pause the video and read it several times, and we'll visualize it instead. In valid transitions coverage, the covered items are single valid transitions. To achieve 100% valid transitions coverage, test cases must exercise all the valid transitions. In our case, the transitions are marked with errors, and many may be confused here. The fact is that the name of the event is always written above the errors, but the transition is not an event. One event can lead to different transitions, which we will talk about a little later. A transition is an arrow, and it affects, in addition to the event, the start and the end states. Therefore, for the sake of simplicity, the diagram looks like the events are the names of the arrows. In fact, it's always better to write a complete table with start and end states. This will help a lot when the diagrams are much more complex. And you can see it in the examples of ISTQB questions. Again, to complicate our task, the test will be written with a sequential list of states. How many transitions do you think such test covers? Open, in progress, closed. This is the same test as in the previous examples. This test covers only 2 of the 3 transitions. Accordingly, the test coverage is approximately 66%. It's clearly visible when we write the extended version of the same test case. The second transition is not covered by the test case. From in progress to open through the reopen event. We need to test it, and we have 2 options. The first option is to add another test, from in progress to the open. We can write such a test because we do not have any restrictions, and nowhere it is said that the test must start in the open state, or end up in the closed state. Therefore, it's very important to carefully read the conditions in the description of the ISTQB question. In the ISTQB question, you have the following typical restrictions. 1. The minimum number of transitions. 2. Each test must start in a specific state. 3. Each test must end in a specific state. We'll check the sample questions later in the video. Long story short, the best practice is to write a test case in such a way as to cover the maximum number of transitions in a single test. For example, we can write one test that will cover all 3 transitions. The test coverage will be 100% with one test. It will be longer because we will have to go through the cycle, and some transitions may be repeated 2, 3, or more times. As it was said before, one test case may and usually will cover several transitions between states. Let's move to the next theoretical aspect of state transition in testing. Again, you can pause the video and read the text several times. We want to discuss this part. All states coverage is weaker than valid transitions coverage because it can typically be achieved without exercising all the transitions. This was clearly visible in our example state transitions diagram. If our goal is to get 100% coverage of states, then we can write a simple test. From open to in progress, from in progress to closed. Thus, all 3 states are covered by tests. At the same time, only 2 transitions out of 3 are covered by this test. As a result, all states coverage equals 100%, but valid transitions coverage equals 66%. This is a fairly common situation for state transition diagrams. After all, mostly in addition to forward transitions, there are also backward transitions. But when our goal is to cover all valid transitions, the situation is different. In fact, it's impossible to write a test that covers all transitions, but does not cover one of the states. As we said before, we need one long test to cover all transitions and achieve 100% valid transitions coverage. And with the same test, we cover all 3 states. Some states even twice. Thus, with one test that covers all transitions, we also cover all states and both coverage. All states coverage and valid transitions coverage are equal to 100%. It's a pretty simple theory, but we wanted to visualize it for you. And now let's look at the new theory that we skipped at the beginning of the video. A state table is a model equivalent to a state transition diagram. You can pause the video and read the text several times. This is a new theory added in ISTQB version 4.0 foundation level exam, which complicates the questions quite a bit. So let's visualize it to make the exam easier for you. Since 2011, ISTQB questions have always included state transition diagrams, the simplest of which we considered with examples above. In version 4.0, a state table appeared. And since there are no detailed examples in the syllabus, students are a bit confused. In fact, this is the same diagram shown in the form of a table. And the same coverage items that we have already considered apply to the state table. First, let's define states. As you can see, they are recorded in a separate column of the table. Accordingly, we have three states, the same as the circles in the state transition diagram. Everything is simple with states, difficulties begin with transitions. As with the state transition diagram, many students mistakenly believe that transitions are events. Accordingly, three events are defined as a transition, which is incorrect. In the case of the state transition diagram, the transitions were not event names, but arrows. For state table entries, cells represent transitions and contain the target state, as well as the resulting actions if defined. So we do have three transitions, but they are not events. In order to better understand this, as in the case of the state transition diagram, it's better to describe the complete chain of events in the transition with three items: start state, event, and end state. Let's describe the first transition, the one in which S2 is written in the cell. We start, as in the case of the state transition diagram, with the start case. The start state in our example is open. The next part of the transition is the event. In our case, the event is start progress. And the last part of the transition is the end state, and it's indicated in the cell S2, which means second state, in progress. Thus, we get a similar transition as in the state transition diagram. We start in open state, the event is start progress, and end in the progress state. We can describe two other transitions in the same way. We will not describe them sequentially. You can pause the video and familiarize yourself with the contents of the table in more detail. In the case of a simple table, we recommend drawing a state transition diagram based on the table. This can help you better understand coverage items and make fewer mistakes. We will make tables for diagrams and vice versa when we consider ISTQB questions. For now, let's consider the last theoretical aspect that remains in the syllable: all transitions coverage, which is applicable only to the transition table. You can pause the video and read the text several times. Let's visualize it the same way as all states coverage and valid transitions coverage. As you understand, all transitions mean valid transitions and invalid transitions. It's very difficult to explain all possible invalid transitions on the state transition diagram. There may be many of them even for a simple diagram. That's why there is a table of states and events. It's easy to determine valid and invalid transitions here. In all transitions coverage, the coverage items are all the transitions shown in the state table. First of all, valid transitions. We have already defined them earlier. These are the ones marked in the cells of the table. In contrast to the state transition diagram, the state table explicitly shows invalid transitions, which are represented by empty cells. Accordingly, there are 6 invalid transitions as opposed to valid transitions for which we do not know the final state. To achieve 100% all transitions coverage, test cases must exercise all the valid transitions and attempt to execute invalid transitions. Similar to equivalence partitioning, we can write one valid test case that will cover all valid transitions. But now the test coverage will be about 33%. After all, only 3 out of 9 transitions are covered by the test. The next step is to test the invalid transitions. And again, the situation is similar to equivalence partitioning. For example, if we want to test the transition from the open state through the open event, then we have to cover only one transition with one test. We cannot write one test for all possible transitions. Testing only one invalid transition is a single test case helps to avoid fault masking, a situation in which one defect prevents the detection of another. Similarly, if we want to test the transition from the in-progress state through the start-progress event, we have to write a separate test again. In our example, we are not limited by additional conditions. But as we highlighted before, in ISTQB questions, you can have the restrictions. For example, each test must start in the open state. This fundamentally changes the situation. Now our test has two steps. And it looks like a small change, but it's actually a very big change if you have a table much more complex than ours. Even for our simple table, the tests for the closed state will have 3 steps each. The complete table of test cases and transitions would work like this. To achieve 100% all transitions coverage, test cases must exercise all the valid transitions and attempt to execute invalid transitions. And we would need at least 7 tests to cover all 9 transitions. The good news is that ISTQB questions almost never ask about all transitions coverage. As you can see, even in our simple example, you need to write at least 7 tests. Imagine if the table has 8 states and 5 events or more, this would make the situation very complicated, and finding the correct answer to a question with such a table or diagram would take much more than 5 minutes. That's why valid transitions coverage is the most widely used coverage criteria. We can see in the examples of questions in all 4 examples of examination tickets available on the ISTQB website. As you can see, the questions always ask about valid transition coverage. Because all state coverage is mostly too simple and all transition coverage is too complicated. However, we cannot guarantee that on the exam you will have a question about valid transitions coverage, so we had to consider other coverages in detail. If you have a question about a large table or with a complex diagram, and in addition to it there will be a table with a bunch of tests, we advise you to skip this question and leave it for the last. All questions are worth only 1 point, and very difficult questions can take a long time. It's better to answer simple questions and come back to difficult ones in the end. There remains one more, the last, and perhaps the most difficult aspect of the theory, which we skipped at the beginning of our explanation. This is also an addition to version 4.0, which can significantly complicate fairly simple questions on state transitioning testing. Let's try to explain this part. A transition is initiated by an event, which may be additionally qualified by a guard condition. So, what are the guard conditions? It's best to explain this with the help of an ISTQB question. There is such a question in Sample Exam B. You can pause the video and familiarize yourself with the state transition diagram. As you can see above, each arrow symbolizes a transition. We have not only the name of the event, but also additional variables and formulas, and it will take a long time to explain. So, let's get started. First of all, we must determine which of the coverage we are interested in: all states, valid transition, or all transition coverage. And as we can see, we need a valid transition coverage. We need the state transitions diagram, with the help of which we will determine all valid transitions, and the table where we'll record them. We start with the start state, which is called start. The event is add n equals 1. For now, we'll write down the event name in full, and we'll talk about the second part of the name in a minute. The final state is not full, and this is what a complete transition looks like. Start, add, not full. Let's figure out what n equals 1 means. For a better understanding, we suggest changing our table a little. To begin with, let's create 3 separate columns: start state, event, and end state. This will help us visualize this complicated theory. Then, let's add two more columns. One will be a guard condition, the other will be an action. The guard condition will be before the event because this is the condition under which the event can begin. And the action will be after the event because it's the result of the event. Let's figure out what n equals 1 means. Is the guard condition or an action? In the syllabus, we can find the common syntax of event with guard condition and action. As we can see, the syllabus recommends writing the guard condition in square brackets and the action through the slash symbol. We cannot guarantee that exactly this syntax will be on all questions, but the general logic is clear. In our case, n is equal to 1. This is action. And now with our table of valid transitions, it's much easier to understand the state transition diagram. The complete transition looks like this. Start state is start. Guard condition is absent. The event is add. Action is n is equal to 1. That is, assigning the variable n the value 1. And the end state is not full. You can pause the video and try to describe the next transition yourself. A specific transition where the start state and end state are the same, not full. We will consider each table cell separately. We hope it's already clear that n is less than 2. This is a guard condition because it's in square brackets. And n is equal to n, add 1. This is action, because it's written after the condition through the slash symbol. In the same way, we have to describe 3 more transitions, and the full table will look like this. 2 transitions do not have guard conditions, the rest all do. Let's now understand how it affects and how much it complicates the question. In the question, we have 4 answer options with sequentially written test steps, and we have to count how many valid transitions are covered by each of the options to determine the correct answer. Let's copy these answer options to the transitions table and state the transition diagram. Let's start counting the number of valid transitions covered by the first step, A. The first step of this test is event add. As you can see, ISTQB questions have many small details that can be confusing. There is only the name of the event, there are no guard conditions or actions. Since we have 2 event names, add and remove, we have to understand ourselves with guard conditions and actions applied to each event in the test. Let's try to do this. First of all, let's indicate the current state of the system using the gear icon, so we'll be able to follow the transitions at the moment we are the start state. From the start state, we have only one possible event and the transition. Event add. This event does not have a guard condition, so we grayed it out. But the event has an action, n is equal to 1. This means that we assign a value to one variable n. We make a note of it and move on to the end state. Not full. It's important to always remember that a test case consists of steps. Each event name is a separate step, and the result of each step is that the system moves from the one state to another. The same way as in our case. Option A covers the first transition, from the start state to the not full state through the end event. Accordingly, the next step will start from this very state, and that's why we leave the gear icon above the not full transition circle. The next step is event remove. Let's figure out which of our transitions it is. First of all, we start with the start state. And this is not full, which is marked with the gear icon. There is only one transition with the remove event. Let's study it more closely. We started with the start state and moved to the event, but the event is complicated by guard condition. N must be greater than 0. We wrote down the value of variable n in the lower right corner of the slide above the gear icon. At the moment, n is equal to 1, which is greater than 0. Accordingly, this is a valid remove event. Now let's move on to action. Action is manipulation with the variable n. N is equal to n minus 1. At this moment, the variable n is equal to 1. Accordingly, 1 minus 1 equals 0. Thus, due to the action of the remove event, the variable n is now equal to 0. We need to write it down. As you can see, the error starts in the not full state and ends in the not full state. Thus, option A already covers two transitions, the first and the fifth. The valid transition coverage is equal to 40%. The third step of test case A is the add event, which corresponds to three different transitions. Since the system is now in the not full state, the number of possible transitions is reduced to 2. We need to check them both. Therefore, both transitions are suitable and both transitions have guard conditions. So we have to check them first. Event add in the third transition has a guard condition. H is equal to 2. In our case, n is 0. Accordingly, this transition is currently impossible, unless we want to test an invalid test case. However, since we have a valid transition coverage, this is not our option. But in the add event, the second transition, the guard condition is n less than 2. At a concrete moment, n is equal to 0, which is less than 2. This means that event add is valid, the system moves to action. Action is n is equal to n plus 1. Now n is 0. 0 plus 1 equals 1, and the value of the variable n accordingly becomes 1. And as in the previous transition, the error starts at not full state and ends at not full state. Thus, 3 out of 5 transitions are covered by tests. The valid state transition coverage is 60%. As you can see, a fairly simple test design technique becomes extremely time-consuming with guard conditions and actions. Don't worry, we are not going to consider all 20 transitions in 4 answer options step by step. Let's finish with answer option A, and then highlight the main details of answer option B, C, and D shortly. So the next step of the test case A is event add again. And since we are still in not full state, the steps are absolutely the same as we just went through. The variable n has a value of 1. Accordingly, the guard condition for the third transition is not suitable because n must be equal to 2. So we test the same transition as in the previous step. You may think that we can skip this step. However, due to the fact that we have guard conditions and actions, we are forced to carefully monitor the variable n. In our case, it's already equal to 2. So the fourth step of the test case tests the same transition as the third step. Because of this, it doesn't affect the coverage of the valid transition coverage. A valid transition coverage remains at the level of 60%. Time to move to the last step. And this is the add event again. We have already discussed the guard conditions of these two add events more than once. However, in the previous two cases, the value of the variable n was less than 2. This time, the variable n is equal to 2. The guard condition n equals to 2 is true. Accordingly, this time the transition is from not full state to full state. Thus, the value of the variable n changes from 2 to 3 due to action in the add event. Action is n is equal to n plus 1. Accordingly, we can see that 4 out of 5 transitions are covered by the test. The second transition is covered twice, but this does not affect the percentage of valid transition coverage. Coverage is measured as the number of exercised valid transitions divided by the total number of valid transitions and is expressed as a percentage. 4 transitions out of 5 are 80%. We note this indicator opposite the answer option A. And we need to consider 3 more answer options. Of course, we will not dwell in such detail on each step of each of the test cases. We believe that we have already explained guard condition and actions in sufficient detail. In our opinion, the easiest way to understand how guard conditions and actions affect the flow state of the transition diagram is with the help of the transition table, which is actually a table of test cases. So, let's quickly consider other options for the answer. The first step of test case B is event add, which corresponds to the first transition. The second step is again the add event. This corresponds to the transition where system starts in the not full state and ends in the not full state. And the value of n changes to 2. The third step is again the add event, and since the value of n is 2, it is the third transition event, where we start at not full state and end at full state. The value of n changes from 2 to 3. The fourth step of test case B is again the add event, but this is an invalid event. The fact is that the system is in full state, and the value of variable n is equal to 3. As we can see, there is only one arrow, one valid transition from the full state. This is a transition from full to not full through the remove event. Therefore, only one valid event from the full state is the remove event. Thus, the add event is invalid. And so are the following events, because we cannot simply skip the fourth step. After the first 3 add actions, the system is in the full state. And there is no valid transition going from full triggered by the add event. After the first 3 transitions, only 60% of valid transitions coverage is achieved. This is all about test case B. Let's check test case C. In our opinion, everything is already obvious. Both guard conditions and actions related to events should be clear. Answer option C covers all valid transitions. Valid transition coverage is 100%. As you can see at first glance, the completely incomprehensible and confusing state transition diagram turns out to be much simpler if you write each transition separately in a table. However, if ordinary questions on state transition diagrams can take up to 1 minute of time, the question that contains guard conditions and actions will take much longer. And of course, it will increase the risk of error. Since the state table is a new concept in state transition testing, we suggest you practice writing such a table to existing state transition diagrams. For a diagram with events that have guard conditions and actions, building a table is not an easy task. The fact is that there are many options for how to record events, and it can be consuming. Therefore, we offer our simple solution to this problem. We suggest always starting with states. As state table rows represent states, mostly, if not always, all have unique non-repeating names unlike events. In our case, there are 3 states: start, not full, and full. Now let's write the events in the table. As state table columns represent events together with guard conditions if they exist. In order not to get confused, we offer provided that the events are not simple, but complicated guard conditions and actions. Record each event in a separate column. This makes it easier to define transitions. Table entries cells represent transitions and contain the target state as well as the resulting actions if defined. In our case, there are 5 of them. And this is what the full table looks like: 3 states, 5 events with 3 guard conditions, and 5 transitions with 5 actions. In contrast to the state transition diagram, the state table explicitly shows invalid transitions, which are represented by empty cells. Coverage is measured as the number of valid and invalid transitions exercised or attempted to be covered by executed test cases, divided by the total number of valid and invalid transitions, and is expressed as a percentage. For example, the same test case that covers all valid transitions and reaches 100% valid transition coverage covers only 33% of all transitions. After all, there are 5 valid and 10 invalid transitions. That's all. We have considered everything related to the state transitions testing question in exam sample B. Let's look at simpler ISTQB question in exam sample A. In the new sample exam version 4.0 document, we can find the following question. Those who want to try to answer the question themselves can pause the video. First of all, we have to find out what the essence of the question is. This is our general recommendation for long questions. Read the question first and then read the full description. Thus, reading the description, you will know what you're looking for and what to pay attention to. As we can see, we are interested in valid transition coverage. As in the previous question, we copy the state transition diagram and create a table where we'll record valid transitions. Since we do not have guard conditions and actions in this example, the table can be simplified without extra columns. As in the previous examples, we must start by recording all valid transitions. The first of which is Start State Initiative, Event Test, and State Debug Mode. The second transition is Debug Mode, Done, Off, and so on. In the previous examples, we have already learned how to define valid transitions, so there is no point in dwelling on this in detail here. The next step is writing test cases. And as you remember, the ISTQB questions can have different types of conditions and restrictions. In our case, we have the following limitation. The system starts in the init state and ends in its operation in the off state. Accordingly, all test cases should start with the init state. And the first step will be the first transition. Init, test, debug mode. As you remember, one test case may, and usually will, cover several transitions between states. Therefore, we can write one more step, one more transition. Debug mode, done, off. Since we have limitations, the system starts in the init state and ends its operation in the off state. Then we cannot write additional steps in the test case, because we are already in the off state. Therefore, we have to start a new test case. As we said before, ISTQB never writes detailed test cases. Mostly it is just a list of states or a list of events. Let's write the test as a list of states this time. So we note that the first test case covered 2 transitions. We record its steps and choose which test to write next. We need to cover 5 other transitions colored red. The choice is obvious. The first step will be the transition. Init, run, in operation. And this time, for convenience, we have again marked the state in which the system will be located with a gear icon. As a result of the first step, the system remains in the operation state. In the second step of the test case, we have a choice. We can cover or transition in operation, error, debug mode, or transition in operation, pause, on hold. In fact, there is no difference because we need to cover all transitions. So let's test the first option. The result of the second step will be that the system will be in debug mode. As you remember, we have limitations. The system starts in the init state and ends its operation in the off state. This means that we have no other choice but to test an already tested transition. From debug mode to off state through the done event, because there is no other arrow from debug mode that would lead to some other state. Thus, with the help of 2 test cases, 4 valid transitions out of 7 were tested. There are only 3 transitions left, and we are starting the third test case. We are again obliged to start from the init state, and thus retest the already tested transition. The second step of the test case is to cover an as yet untested transition, from in operation to on hold. Thus the system is in the on hold state, from which we have 2 options for transitions. We always try to cover as many valid transitions as possible with one test, so instead of going into the off state, we will cover the third step of the transition from the on hold state to the in operation state in the resume of the event. Thus, 6 out of 7 transitions will be covered by the tests. As a result of the third step of the test case, the system is in the operation state. Therefore, in the fourth step, we retest the same transition as in the second step, from the in-operation state to the on-hold state through the pause event. This is a normal situation for state transition testing, where one test case tests the same transitions 2 or 3 times. Well, it's clear that the last 5th step of the test case will test the last 7th transition, from the on-hold state to the off state, the cherry done event. As you can see, 3 test cases are enough to cover all valid transitions and achieve 100% valid transition coverage. And again, as you can see, 1 test was enough to cover all the states. And to cover all the transitions, you need at least 3 tests. Accordingly, the correct answer is D. 3 is the minimum number of test cases to achieve valid transition coverage. As you can see, when there are no guard conditions and actions, ISTQB questions related to state transition testing are quite simple. And you can find the correct answer to them, sometimes even in 1 minute, if you practice enough. But this is not the end of our tutorial. As in the previous question, let's practice building a state table to the state transition diagram that was in the ISTQB question. You can pause the video and try to build a table yourself based on the state transition diagram. Since there are no guard conditions and actions this time, it will be much easier to do. A state table is a modal equivalent to a state transition diagram. Its rows represent states. We have 5 states, which are rectangles on the diagram. The next step is to define events. A state table columns represent events, together with guard conditions if they exist. The names of the events are written above the arrows, and we have 6 of them. Pay attention to the fact that there is a done event, which is repeated twice. But in the table, we record it only once. The third step is the definition of transitions. Table entries cells represent transitions and contain the target state, as well as the resulting actions if defined. We have 7 transitions in total. The full transition table looks like this. You can pause the video and analyze it. Once again, we want to emphasize that transitions are not events. What is clearly visible in this example? There are 6 events, but 7 transitions. Transitions are arrows. In contrast to the state transition diagram, the state table explicitly shows invalid transitions, which are represented by empty cells. In all transitions coverage, the coverage items are all the transitions shown in the state table. To achieve 100% all transitions coverage, test cases must exercise all the valid transitions and attempt to execute invalid transitions. Accordingly, if we had the same 3 tests that would cover all valid transitions, then all transition coverage would be only 23%. After all, there are 7 valid transitions and 23 invalid transitions. Let's look at another example of ISTQB question that concerns state transition testing. In the new Sample Exam version 4.0 document, we can find the following question. Those who want to try to answer the question themselves can pause the video. This time it's not a question with a state transition diagram, but a state table. As in the previous 2 questions, we are dealing with valid transition coverage. This time we have 4 test cases, A, B, C, D, and we have to determine which one covers more valid transitions. As in the previous 2 tutorials on answering ISTQB questions related to state transition in testing, we create a table of valid transitions, but the difference is that this time, instead of analyzing the state transition diagram, we need to analyze the state table. Let's begin. Table entries cells represent transitions and contain the target state. The first such cell is S2. In fact, it's no different from the arrow on the state transition diagram, about which we will talk a little later. For now, let's learn to understand and analyze the state table without the state transition diagram. So, we start with the start table. A state table is a modal equivalent to a state transition diagram. Its rows represent states and the start state, in our case, is requesting. Since the state of the system changes with each transition, we will mark it with the icon of a customer who checks a hotel room. so it will be easier for you to follow the current state of the system. The next step is to define the event in the transition. In state tables, columns represent events. So in our case, the event is available. As we said before, table entries cells represent transitions and contain the target state. In our case, S2 is written. S2, this is the second state from the rows of the table. That is confirmed. Therefore, the end state in the first transition will be confirmed. And the complete transition will look like this. Start state, requesting. Event, available. The end state, confirmed. It's clear that we will not consider all 7 transitions in such detail. You can fill them yourself. The second transition will be start state, requesting. Event, not available. End state, waiting list. And so on. In the same way, we can define the start state, event, and end state for all 7 valid transitions. And now we can get to the heart of the question. We need to determine how many valid transitions each test case covers. And as you already know from the first ISTQB question, this is a very time-consuming activity. Therefore, we will consider in detail only the first answer option, A. So, since the test cases are recorded in a simplified form, a sequential set of events, we suggest adding another table for visualization, where we'll record the full version of the test case. As we have already emphasized twice or 3 times, ISTQB questions always have certain limitations, clarifications, or conditions. This time, there is a condition. The test cases start in the requesting state. So, the start state of the first transition is requesting, which corresponds to 2 possible transitions. However, the steps of shortened test cases are events, and the first event is not available. And this corresponds to only one of the valid transitions, the second in our table. In the second transition and state, there is a waiting list. Accordingly, the user icon moves there. We note that test case A covers exactly the second transition, start state, requesting. Event, not available. End state, waiting list. And we can move to the next step. The next step is the available event. However, we suggest starting not with the event, but with the start state. And in our case, the start state of the second step of the test case is the waiting list. It was there that the user ended this journey after the first transition. We mark the state with a red icon. As you can see, there are 2 transitions in our table that begin with the waiting list state, 6 and 7. However, we know that the second step of the test case is the available event itself, which corresponds to the 6th transition. Now you need to determine the end state. As we can see, S2 is written in the cell. This means that we are interested in the second line in the state column, which corresponds to the confirmed line. Accordingly, the icon of the end user is moved there. Thus, the second step of the test case covers the 6th valid transition in our table, and we can proceed to the 3rd step. We will not study each of the transitions in such detail. The 3rd step of the test case covers the 3rd transition in our table. Accordingly, the user moves back to the request state. The 4th step of the keys test repeats the 1st step. This is the same transition from the requesting state to the waiting list. And the last 5th step test case covers the last 7th transition in our table of valid transitions. Accordingly, the user did not wait for his room in the hotel. Thus, the first test case, answer option A, covers 4 transitions out of 7, which is roughly equal to 57%. And in the same way, we need to test 3 other test cases, B, C, and D. Since the number 7 is not convenient for calculating the percentage of test coverage, it's easier for us to record exactly the number of valid transitions covered by the test. 4 out of 7. And of course, we will not consider the other 3 answer options in detail. Let's just make a small summary for each. Answer option B covers 5 transitions out of 7. Although these are not all transitions, they are more than option A. Each step of test case covers a separate transition, and it's clear that this is our correct answer, because more than 5 cannot be covered in 5 steps. Answer option C covers only 3 transitions out of 7. It makes no sense to stop and discuss it at all. It's not a serious candidate for a valid answer option. And answer option D is generally invalid. After the first 2 steps, the user finds himself in the end state, that is, he left the hotel. Accordingly, the user cannot perform the change room event. Only 2 transitions out of 5 are covered by tests. As we said, if you only have 5 steps and each step represents a transition, so you cannot cover more than 5 transitions with a test case. Accordingly, answer option B is the correct answer option. As you can see, the question related to the state table is not so difficult. It would be much more complicated if there were guard conditions or events in this table, but not in this case. And that's almost the end of our tutorial. We suggest trying to build a state transition diagram based on the state table in order to better assimilate the studied material. And it's done with the same steps as before. We start with states, we have 4 of them. Accordingly, we draw 4 circles. Of course, you would first draw them in a row. But since we already know how the diagram will look, we drew the state waiting list in a separate row in advance. The next step is to draw arrows that represent transitions. In the state table, table entries cells represent transitions and contain the target state. So each cell of the table will be a separate arrow. We write the name of the event above the arrow. And in this way, we get a rather complex diagram. We hope this makes it easier to understand the relationship between the state table and the state transition diagram. And this is the end of our long and complex tutorial on state transition testing. We hope that our visualizations of the theory from the syllabus will help you better understand what is written there. And it will be easier for you to answer the questions on the exam, because one of them is guaranteed to be devoted to the state transition testing. For the topic black box test techniques, we have about 50 questions in total. About 10 of them will be related to the section State Transition Testing. It's more than enough for practice. Well, that's the end of our today's tutorial. And we hope to see you in the next lecture.